I'm Ryan Marcus. I'm a postdoc at the CCL lab. I work under Tim Kraska, and our lab's recently been doing a lot of work about machine learning for systems and those sorts of concepts. Today, like Andy, I want to give a pessimistic talk about query optimization and deep learning. If you looked around the room today, you would think that machine learning has a pretty friendly reception at database venues. But if you were publishing maybe 5 or 6 years ago, that kind of perception was very, very different. Like you could not submit a paper with machine learning in it without a reviewer comment about how there wasn't a worst case bound or how it didn't handle arbitrary data or something like that. Luckily, or unluckily, depending on how you see it, the AI winter came to an end, and the systems community was more or less forced to start paying attention to what was going on in machine learning. That may sound like kind of a nasty version of events, but for those of you who were around 5 or 6 years ago, I promise you remember. So luckily, we came to our senses, and there's been a recent just huge groundswell of work in terms of using deep learning for query optimization. There's been a lot of, there's sort of two categories of work in this space. One is a reinforcement learning based approach, where you sort of try to optimize for query latency directly, and another is a more cardinality estimation based approach, where you try to find good cardinality estimates to give to the cost model in the optimizer, because that's like 80% of the battle right there. Unfortunately, all of these works, and I'm including my own, suffer from this problem where they're sort of just add deep learning and stir approaches. So specifically, a lot of these models are overly reliant on fully connected neural networks. They have issues with train test set split leakage. They tend to either use off-the-shelf reinforcement learning algorithms or standard off-the-shelf regression loss functions. They don't really integrate well, or possibly even at all, with a broader database management system. And a lot of these papers don't actually have an evaluation of how their system changes actual query performance in terms of query latency, right? Like just because your cardinality estimator gets better doesn't necessarily mean your query plans got faster. So I started calling these the 5 deadly sins of machine learning for query optimization. And again, a lot of my work falls into this category as well. I'd love to talk about each one of these, but today I really just want to focus on why we should, as a community, maybe view any work that's mostly a fully connected neural network with a lot of skepticism. So in order to do that, sort of set the stage for that argument, I want to talk about why deep learning has been so successful, right? And if we look at sort of the history of how the field developed, it's really seen massive success in 2 specific areas: computer vision and natural language processing, or CV and NLP. So if we look at the architectures that have primarily been the main driving force in those 2 fields, those are convolutional neural networks, where you learn tons and tons of tiny little filters that sort of slide themselves along an image and detect features, and long short-term memory networks, or LSTMs, which can remember stuff from the past, but also forget that information. And what's unique about both of these architectures is that they really only have fully connected layers at the very end of the network. Like these aren't like large multi-layer perceptrons stacked on top of each other kind of things. These are very specific tailored architectures to the problem at hand. Now, the general strategy that was so successful in both of these cases was, in the computer vision case, to build a neural net to recognize objects and images. They modeled the low-level structures that were used by the human eye, right? They looked at the actual human visual system, the actual optic nerve, and what it was doing. And they designed a process that was biologically plausible, but differentiable. And that led them to the convolution layers for neural networks. In the same sense, in natural language processing, to build a neural network that would recognize words, for example, in speech, they modeled the low-level structures that were used by the human prefrontal cortex for those kind of speech processes, right? This sort of idea of a forget gate and a neuron that activates eventually, that sort of thing. The general pattern here, which we can extrapolate, is to build a neural network to perform some task X, we should model the low-level structure used by some expert system known to perform well, right? This is known as an inductive bias. When you take your network architecture and you shape it in a certain way so that the possible functions your neural network can learn are limited or constrained in some way. Now, as systems people, when we hear every time you have a specific problem, you should design some complex architecture around it and then train that complex architecture, we say, you know, thanks, I hate it, right? Like, we don't want that at all. As systems researcher, we hate these complex problem-specific solutions. What we want to do is we want to throw out complexity. We want to create systems that generalize, right? So we want to think like, okay, is there something that's like a convolutional neural network and like an LSTM, but like it's both and I don't have to pick between the two, some kind of like holy grail of architecture, right? And you might think, oh yeah, right, there's this famous result from a long time ago about neural networks that showed that fully connected layers can represent any arbitrary function that you want. Unfortunately, this doesn't work very well, right? Imagine you're trying to train a model that correlates temperature with ice cream sales. If this is your original data, here's two possible functions you can learn, right? Arbitrary function A and arbitrary function B will both have the exact same loss, right? PyTorch will be equally happy with both of these functions that you learn to fit, and yet we should probably prefer one of them more than the other, right? We don't want to fit an arbitrary function. We want to fit a generalizable function, right? A fully connected neural network can represent an arbitrary function. We don't want that. We want a representation of a reasonable function. Now keep in mind, this is not just about overfitting, right? In old school ML, the way that we deal with overfitting is through things like regularization and cross-validation. No one does cross-validation on deep learning, it takes too long. People sort of do regularization, maybe they do like an L2 weight penalty here or something, gradient clipping or something like that, but not really, right? With deep learning, we're not doing tree pruning, we're not doing lasso, we're not doing any of these techniques designed to simplify our functions again, we're just doing SGD, which means that this arbitrary function A is totally a valid result that your multi-level perceptron fully connected network could learn. It's completely acceptable. Nothing is stopping it from happening. There's no deep learning magic whatsoever that makes a fully connected network more likely to give you function B than function A. Pop quiz, see if you're paying attention. Imagine I'm trying to rank MNIST performance with a couple of different machine learning algorithms. On one of them, I'm going to use a fully connected neural network, which is a universal function approximator, woohoo. Then I'm going to use a convolutional neural network, designed to have a good inductive bias. And finally, I'm going to use a random forest. Now, you might think, based on the number of papers that simply use fully connected neural networks that you may have seen published at database conferences, that the fully connected network would at least be in first or second place, but in reality, it's not. The convolutional neural network obviously does fantastically on this task. That's what it was originally designed to do. The random forest comes in second, and the fully connected network is kind of a distant third. Now, the reason that this is happening is because of inductive bias. Convolutional neural networks have a very strong inductive bias that we borrowed from the human visual system, right? They have to learn these little sliding windows of filters. There's nothing else they can do. Random forests also have an inductive bias that's normally called conditional sparsity. If you're training a random forest model and you split on one pixel, because pixels and neighborhoods are highly correlated, you're very unlikely to split on the pixel next to it. Now, fully connected neural networks, again, also have an inductive bias, but that inductive bias is to assign every input feature a weight, no matter what, right? Take every single pixel inside of my entire image, give it a weight, multiply them and add them up, and now do that a whole bunch of times. Yes, it can learn any function, but as we've seen, it's not going to learn the function that you want very well, because it's just going to kind of learn the first function that fits. It's not going to have a good inductive bias. It's not going to model the systems that we know are good at visual learning. The conclusion from this that the deep learning community has had for a while, and that hopefully we as the systems community can start having very soon, is that deep learning is fantastic if and only if the inductive bias of the model matches reality. If you're trying to teach a computer to see, the neural network architecture that you use has to be good at seeing things. Similarly, if you're trying to get it to hear or optimize queries, the architecture of the neural network needs to know about that somehow. You need to find a way to encode that knowledge in the network. So all of the deep learning hype, all of this, stuff we get excited about, like end-to-end training, like automatic feature engineering, and super good generalization. In reality, we can have all of these things, but you have to get the architecture right? If you throw a fully connected neural network at a problem, like MNIST, you're going to get worse performance than your traditional ML techniques like random forest. So what about database systems? We know that convolutional neural networks work well for computer vision, but what are we going to use inside of a database system? Obviously, I don't have an amazing answer to this question, but I do have one proposal, which I've been calling tree convolution. So if we looked at how LeCun and others went around designing convolutional neural networks, they looked at what the eye did at a very, very low level. So we can sort of replicate that process for ourselves by looking at what we, as database experts, do when we're trying to examine the performance of a query plan tree, right? So if I showed you this query plan tree right here, you'd probably make a couple of observations. One of the observations you might make is, okay, you have a lot of stacked sort operators, right? You have a lot of sort operators in a row. That's probably good, because you're probably going to get a nice pipelined query plan with a lot of merge joins in it, possibly without any resorting, right? Assuming your keys line up. If instead I showed you this query plan, you might say, ooh, you've got a lot of sorts on top of hashes, sort hash, sort hash, sort hash. I don't know why you picked this, but I can guarantee you in between each one of those join operators, you're either going to have to rehash sorted data, or you're going to have to sort hashed data, right? So that sort of pattern, it really doesn't make sense. Now, if you're a DBA and you're really familiar with this data, you might know that the appears in relation is pre-sorted on disk based on a key. If that's the case, then you probably know, oh, well, this thing's already sorted on disk, it's got this clustered index, it probably shouldn't be going into a hash join, it should probably be going into a merge join. And the pattern behind all of these observations is that we as experts examine the local structure of the tree first, right? Like we spot something like a sort on top of a hash or a sort on top of a sort. And then we extrapolate that to higher level features, a whole chain of sorts, or an alternating chain of sort hash, sort hash, sort hash. Or we notice higher level features like, the appears in relation is going into a hash join. So these are the kind of things that we as human beings notice. Now, I've got a reasonably sized check, the best of postdoc salaries can offer, for anyone who can explain to me how a fully connected neural network captures that intuition. Instead, what I argue captured this intuition a little bit well is an idea of tree convolution. Just like how we have little 3x3 oriented edge filters and color filters for images, we can also sort of think about, okay, well, what would a filter that we slide around to examine local structure look like on a tree? So for example, I've shown, here's a very basic filter that's going to detect a hash join that's on top of a sort join. And if I run this filter over the query plan tree on the left, I do that by first taking this little template and lining it up with the top of my tree. So the hash, the purple boxes match, the red, the sort those boxes match, and C is 0, so we assume that's 0. So we get 2 matches out of that. Then we slide the tree down, the sort's not a hash, A is not a sort, B 0, we get a 0 again, and we can continue to slide this whole thing around the tree until we get a complete example. So now we've built, using just 3 parameters, a feature detector that will find a hash on top of a sort anywhere in our query plan tree. Right? We no longer need to have one neuron in our fully connected layers for each and every time this could possibly happen. Instead, a single filter can detect this feature anywhere in our plan tree. Of course, you can generalize this quite easily. Here's an example of a filter that looks for B on the right-hand side going into a merge join. Right? When we take this filter and we slide it over our tree, we get more things that are different. Right? We get a 2 in a different location because this thing is serving as a detector for something else. So just like image convolution, these things are stackable and composable, right? I can take multiple layers of tree convolution because they're an operator that map trees to trees, and I can stack them together, which is good. Just sort of, I'm not going to go into like how well this works now, but we have built an end-to-end reinforcement learning powered optimizer. It's called NEO. You can see the talk on Thursday. And what's critical about tree convolution is that almost any tree convolution filter is going to be close to something semantically relevant. It's going to have some kind of meaning in terms of what you or I think of in terms of the space. So you might be thinking, okay, this idea of inductive bias is great, but you haven't told me if there's a test for it. You've just sort of said that some networks have this thing called inductive bias, and other networks don't have this thing called inductive bias, so what is it? I don't have a good answer for you. I don't have like a magic algorithm that will look at a neural network and tell you if you found a good inductive bias for your problem or not, but I do have a test, and it's called the random weight test. Now, this is a sufficient but not necessary condition, meaning that if you pass this test, you definitely have a good inductive bias, but if you fail it, you may or may not. Here's what it is. You're going to take your model, you're going to randomly initialize all of the weights in it except the last layer. Then you're going to train only the last layer and test your model's performance. So for example, in a fully connected network, I'm going to set all of those things that I have in the little group operator randomly, and I'm only going to train the last layer's outputs. For the convolution, I'm going to set every convolution filter to something totally random, train only the last layer. For the random forest, I'm going to pick all my splits randomly except for the last layer. Now remember, our original accuracies when we trained end-to-end for these are shown here, 86, 98, 92. If I only train the last layer, these accuracies look like this. So the takeaway from this that you should be noticing is that there's a really big gap for the fully connected network, which means most of those random weights that you chose in your fully connected network weren't super helpful, right? Training the whole network gave you almost a 40% bump over just training the last layer. If you look at the convolutional neural network, even if you randomly initialize all of your filter weights and just train the last layer, you do better than training the fully connected layer all the way through. It's the power of a good inductive bias, similar findings for random forest. So the takeaway here, even randomly initialized convolutional layers perform better than trained fully connected layers because you got the inductive bias right. No amount of extra data, no amount of additional parameters, no amount of fancy AutoBoost algorithms will ever make up for having a good inductive bias. We should take that, we should write it down in the query optimization, machine learning for query optimization Bible. So for us, this is a bit of a spit take, right? Because we're used to the generalized systems performing better than the specific ones, right? We write a SQL database that works way better than whatever ad hoc C code that you wrote, right? So this is surprising, and we should pay attention to it, because it means deep learning isn't just something we can add in and stir and it's all magic. It means we need to pay attention to how we architect our networks. So in conclusion, deep learning and computer vision and natural language processing have had huge success because of well-designed inductive biases. If you see a fully connected layer that's giving you a level of generality, that might actually be bad, might actually be hurting you. And finally, finding the right inductive bias for your problem is probably the biggest single thing you can do to get more leverage from a network. That's it.
Any questions?